Everybody's heard of acids and bases before, but we're finally going to get some rigor on what exactly an acid or a base is. At least we're going to get some rigor, because there's going to be some additional definitions, and we're not going to go on to all of those definitions. We're going to stay with a simplified definition called the Arrhenius definition, after a person named Arrhenius, and I'll leave the history of that for other sessions. And in that definition, we're going to say that an acid produces H plus when dissolved in water. You can also write this as HX. I like to say as HA. Different books will sometimes write it as HX. The reason I like this better is because when you have your anion written as A minus, it really helps you remember that that's a generic anion. It also helps imply that when paired up with H, it ends up being an acid, and reminds us that we're going to have our H plus form from that. That's the kind of thing we're talking about there. Now the thing is, a lot of the ones that we're going to see for these are going to be things that we would have thought might be covalent back when we did our examples with the Lewis structures. In fact, if I go ahead and I put a bond right here, instead we look at hydrogen and chlorine. Remember that hydrogen's electronegativity is 2.1. Chlorine's electronegativity isn't as high as 4, that's fluorine's. So even without knowing the exact number, and it's in the mid-3s, even without knowing the exact number, we know it's less than 2. We expected this to be a polar covalent bond with the polar arrow drawn like that. So why is it that this is dissolving in water? Well, simply put, when the water is present, the water can help pop loose this proton when multiple water molecules grab hold of the partial positive charge over here on hydrogen, with that partial negative charge on the oxygen of the water molecule. So just to make that more visual, and remember that your positive charge will be down here, your negative charges are up there. That's what the polarity of this looks like. This oxygen can stick to this hydrogen and help pop it loose. So these are going to be acids as a result. Even though we called it a covalent bond, the hydrogen is able to pop loose when water's around to help that happen. Now, strong acids, and remember, strong tells us that 100% of the time it dissociates. Weak would tell us that less often than that it dissociates. So a strong acid is a strong electrolyte. A weak acid is a weak electrolyte. Hydrochloric acid, HCl, and we'll learn this in other videos, this is going to be a strong acid, which means that when it hits water, 100% of these will be converted into H plus and Cl minus. So that's what we're talking about when we say strong acids. For a weak acid like acetic acid, the one in vinegar, it's not going to be completely dissociated. Some of them are going to stay with the H plus attached to your acetate ion. Some of them are going to be totally separated to be the H plus and acetate ion at the same time. Now, that idea should hold true for bases, right? And absolutely. In this case, a base is going to produce OH minus when it's dissolved in water. Now, if you've watched your solubility videos, you also know that there's a whole lot of cases where the hydroxide ion ends up being a solid. So you really got to pay attention to which ones you're dealing with when you're deciding if it's whether it's a base or whether it's a solid that precipitated, because those are going to matter a lot. But sodium hydroxide is one of the ones we talk about all the time as a strong base. NaOH. And it's going to give you Na plus and OH minus when you dissolve it in water. It's a strong base, so 100% of the time sodium hydroxide pops apart and gives you OH minus. The funny thing is, there really aren't any weak bases that are like that. Any of the things you're going to have where you've got a cation, they're going to be metals, right, attached to an OH minus, they end up precipitating. NH4 is the only exception. So think about all the cations that you know. All of the cations you know are either going to be metals, or they're H3O plus, which we've just talked about as an acid, or NH plus, right? Or they're NH4 plus. And it turns out NH4 plus is the one other case. You can have NH3, ammonia. It grabs the hydrogen off of water. By doing that, it left behind the OH minus that you see right down here. So unlike acids, where you're always going to have an H plus in the strong, you're always going to have an H plus in the weak. In strong bases, you'll have an OH minus. In weak bases, the formula for the base does not have an OH minus, but by taking a proton away from the water molecule, it generates OH minus. And because it has to make it on the fly, it doesn't do it 100% of the time, and that makes it a weak base. We'll also find out in advanced versions of the definitions for acids and bases that there are other kinds of bases, and now we're talking about electron donation or electron accepting. That's not something we're going to bring up in our course, though.